try to complete the topic in the next 2 hours. All right. So are you able to see the screen?
Yes, sir.
Okay. So we have already discussed about the types of state machines, the Mealy machine and the Moore machine. We have also discussed the differences, and we have also seen that each one of the machines has got its own unique use. Depends on the applications, which machine is best suited for you. At the same time, we also said that using Moore machine, it is guaranteed that metastability condition is avoided as much as possible because everything is synchronized to a clock. The outputs are synchronized to a clock. Whereas in case of Mealy machine, it is quite possible that whenever the inputs arrive, the outputs will change irrespective of the clock. And so maybe the next stage, whatever you are cascading it with, probably may have metastability issues. Okay. So we yesterday saw what is called as a state diagram. So when you are going to represent the state machine, a very simple and graphical way of representing the state machine is with the help of a state diagram. So this is an indicative of a very simple state diagram where a state machine where you have only 2 states over here. We're going to see more details about this. This is basically the design flow for the FSM. I want all of you to copy this down. I hope some other people also have joined the meeting. Not yet. Doesn't matter. I'm not going to wait for students any longer. It has become a practice to join late. Anyways, so I hope you copy this down. Siddesh?
Yes, sir. I'm writing.
Yeah. Tell me once you have finished. So whenever we start design, it's always with the word description of the circuit behavior. In simple words, it is the specification. The word description has to be converted into specification. That part is already done over here in this case. So we specify the problem. It is nothing but the word description of the circuit behavior. We start with derivation of the state diagram. Okay, the one that we have already seen. Similar kind of state diagram has to be drawn. Then from the state diagram, you obtain what is called as a state table. Okay, we are going to see all these things the conventional way, and then we are going to shift over to VHDL so that it maintains the completeness. Then we go for what is called as the state reduction. Many states can be or may be redundant or superfluous. So in that situation, state reduction will be necessary. That also will reduce the number of flip-flops because subsequently you will see that the number of flip-flops is equal to the number of states. Okay, that also is there. So then you go for what is called as the next state, which is the determination of number of flip-flops which are required. And the type of flip-flops has to be chosen. From that, you have to derive what is called as the excitation equation. And then using K-map, you can derive the output functions and the flip-flop input functions. Okay, and then finally you draw the logic diagram. So these are the essential steps in designing the finite state machine. Have you completed drawing it?
Yes, sir.
Okay, the flow, design flow. All right. So let us look at a very simple thing called as a rising edge detector. Okay, it may seem very simple, but it is the most easiest example to start with the state machine design. So what basically is expected of the rising edge detector is that there are 2 states, obviously. One is when the output is low and the one when the output is high. Now these are the 2 states and we are supposed to, let us say, detect the rising edge of the clock. So there are 2 states, high and low. Look at the notation next to the arc between the states, which stands for the input/output relationship. That is values during the state transition. Now the machine will go from low state to high state, but while going from low to high, you have one unique combination of input and output, whereas from going from high to low, again you have a unique combination of input and output. Okay. Similarly, if you don't want the state to change like this, it remains in the same state. Again, you have a unique combination of input and output. So first of all, understand the diagram properly. Okay. These arrows or the arcs, they describe what is called as a state transition. Okay. So how do you read such a kind of state machine, state diagram? Okay. You see that the machine advances to the next state when it sees an input X, and at the same time the machine also outputs Y. So what does this indicate? This one, this particular state transition, what does it indicate? That when the state machine was in low state, and when we got the input as 1, it goes into the next state, and at the same time the output of the state machine is 1. You able to understand this?
Yes, sir.
Siddesh, are you able to understand this concept?
Yes, sir.
Okay. So whenever you see a state diagram like that, it is basically you have to read it properly. Unless and until you read the state diagram properly, you will not be able to go ahead with the design. Okay. Then we have what is called as the state table. Now I have come out with a unique way.
Sir, screen is not visible.
Screen is not visible? Is
Yeah,
it?
it came now. Yeah, it is visible now. I
Okay.
think there was drop in between.
Okay. Now, are you
Yeah,
able to
it's
see the
visible.
screen?
It's
What does it
yes, sir.
show? What does it show?
State table.
Okay. So you can understand one very important thing, that I have simplified the state table itself. The next step was the state table. The first step was drawing the state diagram. Next step in your design is the state table. Okay. So how do you derive the state table? How do you put it in a proper way? So for that, I have devised a very simple way. Many books actually combine uh, the table in a particular way, which can be a little bit confusing. But here I have um, modified the conventional state table, and I have shown a unique way of describing the state machine or the state diagram in terms of the state table. Okay, let us first of all understand the table. Okay, look at the first column. The first column gives you the present state. The first column is the present state. The next column, there are three major columns: present state, the next state, and the output. Okay, these are the major columns. Do you understand that?
Yes, sir.
Okay. Now, in that next state column and the output column, I am having sub columns or the subheaders indicating the inputs. So, next state when input was so and so. Next state when input was so and so. So, since there are two possible values for I, that is the input, it can be either 0 or 1. So, correspondingly, you have two sub columns here. In next state and output columns, you have two sub columns corresponding to the input combinations. Now, since you are having only one input, you will be having only two columns over there, two combinations. Either I will be equal to 0 or I will be equal to 1. Similarly, here I equal to 0 or I equal to 1. Now, let us try to understand how to populate this table from the state diagram. All right. So again, one peculiar thing that you should notice is what is the number of the rows in the state table? What is the number of rows?
4.
4. So this actually corresponds to these 4 transitions, 1, 2, 3 and 4. Okay?
Yes. Okay, sir.
Is that fine?
Yes, sir.
Okay. Now each one of them I have color coded so that it is easier for you to understand. So let us take, okay. So two such transitions happen when the state was low, namely this transition and this transition. Okay. Similarly, two transitions happen when the state was high, that is the current state or present state was high, that is this transition and this transition. Okay. So that is the reason why you have low here, again low here, high here, and again high. First of all, understand this. 4 rows correspond to the 4 transitions. Okay. Is that fine?
Yes, sir.
Okay. Now, how do you populate this? A very simple way of doing it is when the present state was low, we will start with this particular transition. Are you able to see this? This transition.
Yes,
There is
sir.
no transition per se. That is the state is remaining same. The next state is also going to be the same. Even input is 0, and at the same time the output should be also equal to 0. So let us see how you populate this. Sorry, how you populate this state table. So when the present state is low, and the input is 0. Okay, what should be the next state? When present state is low, input is 0. What should be the next state?
Low state.
Low. So you put low over here. Okay. Similarly, when present state is low, when the input is 0, what should be the output?
It will be 0.
0, isn't it?
Yes.
So this is the way in which we will populate the state table. Okay, let us have a look at the second row. Okay, so in the second row, when the present state, this one, when the present state is low, but now it has, the input has asserted to 1, the input is 1. What should happen? What should be the next state?
High state.
So put an arrow like this. When the present state is low, input is 1, next state is high. But at the same time, when the present state is low, input is 1, what should be the output?
It should be 1.
It should be 1. So I'm writing 1 over here in this table. And similarly, you can just populate the other rows of the table as well. So when the machine was in high state, okay, and when input was 0, for example, okay, when the machine was in high state and the input was 0, what should happen? Next state should be 0, so it is jumping to the low state. Okay, at the same time output should also be equal to 0, so high, input 0, output should also be equal to 0, the yellow row or transition. Again, when the input is, when the present state is high, but at the same time input was 1, input was 1, what should be the output? Rather, what should be the next state? It should remain in the same
Next state
state.
is same. Same state, yeah.
Okay, and when the input is 1, when it was in state high, output is 0. So do you understand how this table is created?
Yes, sir.
Very basic things, but very, very important ones. Okay. So there is a
Yes,
template
sir.
which I have created here. How do you make a row entry? When present state is low and input is 0, the next state will be low and the output will be 0. This is a template. Now from the state machine, from the state diagram, you can create the state table. So have you understood the creation of state table now?
Yes, yes, sir.
Simple, it is very mechanical that way. This is the timing diagram. to understand what exactly goes on as far as the waveforms are concerned. So we'll have a very crude animation here. So our present state is low, your input is 0, output is 0, and the present state is low. Now when it gets the input here, so when it gets an input 1, output should be equal to 1, and the state should change to high. This is what exactly it is doing. Try to understand this timing diagram also. Now when the state is high, but at the same time, even if the input is 1, it should remain in the same state. What should happen? Remember always that everything is happening with the clock. Okay? Everything is happening with the clock or the rising edge of the clock. Understand one thing, that this machine is supposed to detect what? What is it supposed to detect?
Right.
Rising edge
Rising
of
edge of the
what?
clock.
Of the clock.
I know.
It is not supposed to detect the rising edge of the clock. It is supposed to detect the rising edge on the input signal. This one. Don't get confused.
Yes, sir.
Okay. So this is the input signal whose rising edge we want to detect. This clock is independent. Okay. This is simply driving the state machine. Okay. So when the machine was in high state and input was 1, it was staying in the same state. But when the input was 0, what should happen? You'll see that on the next occurrence of the clock cycle, the state has changed here. The state has changed and the output will be 0 again. So this is how you describe the timing diagram. Is it fine with you?
Yes, sir.
Okay, and again, when it was in the low state and if there is no assertion of input, that is input stays 0, output should also stay 0. That is what is depicted here. There was no rising edge detected on input signal, and so the output was equal to 0. Is that fine?
Yes, sir.
Okay. So have you understood this timing diagram properly?
Yes, sir.
All right. So the next process is test state encoding. So here what we are going to do is we are going to assign the binary patterns. Uh, for the binary patterns, we are going to assign zeros and ones, and those will be the state variables. Okay. So every state has to be encoded. Okay. So that state can be encoded in binary pattern. There are various ways in which you can do it. One is the binary encoding, another is called as the one hot encoding, and the third one is called as the gray code encoding. Of course, we will not discuss gray code encoding here, but I hope all of you know what is binary encoding and one hot encoding. What do you mean by binary encoding and one hot encoding? Have you ever heard of these things? Siddesh?
Not heard about actually one-hot encoding.
You have not heard about one-hot encoding. Okay.
Ye-
So what do we do in binary encoding? This is a common form of state assignment. This is a very logical thing, and it requires minimum number of flip-flops. So each of these states, okay. So for example, um, in our situation, the state machine, how many number of states were there? How many number of states were there?
Uh,
Only two
Two
states,
states. High and yes,
isn't it? Only two states.
yes.
Now I can use one flip-flop over there because I'm having only two states. I can use one flip-flop because one flip-flop either the output can be 0 or 1, isn't it? So the two states can be distinctly, let us say, represented. Are you able to understand this?
Yes, sir.
So I can use only a single flip-flop there. But for example, if there are four states, how many number of flip-flops will be required? It is right there in front of the screen.
Four state.
There will be four
Flip. Two
states.
flip-flops.
So two flip-flops corresponding to that. Okay, because two flip-flops can give a combination of four patterns, binary patterns, that is 0, 0, 0, 1, 1, 0, and 1, 1. Similarly, three flip-flops can be used for assigning how many states? 8 states, 2
Eight
to the
Eight
power.
states.
state.
Okay, so it is going to be something like that. Okay, so the number of states, if you have, let us say, number of states, n number of states, the number of flip-flops will be required to be ceiling, that is the upper value log to the base 2 of the number of states. Are you able to understand that? Yes.
Yes, sir.
Yes, sir.
Suppose there are 17 states. How many flip-flops will be required? Yes,
Five.
5, correct. Why? Because 4 cannot be sufficient. 4 will be insufficient
Limited.
over there. So the next number happens to be 5. 2 to the power 5. So there will be actually 32 possible combinations, out of which 17 can be used for our state machine. All right? Is that fine?
Yes,
Yes,
sir.
sir.
Okay. The other way of encoding is called as a one-hot encoding. Now this is another preferred way. Each state will be represented by an individual flip-flop. But one downside to this is that the number of flip-flops would be required will be more. Okay, but at the same time, the advantage is that it gives you a faster state machine because the because it can operate at higher clock frequencies. So what is one hot encoding then? If you have four states, how many flip-flops will be required?
Four
Four
flip-flops.
flip-flops.
Four. And how will you represent them?
Uh, each state by each flip-flop.
Yes. So how do you do that? So for example, in earlier situation, you had something like 0, 0, 0, 1, 1, 0, and 1, 1. So each one of them was giving you four states. I mean, each one of them was giving you a single state. So four over here. In case of one hot encoding, what would be the scenario? It would be 0, 0, 0, 1 0 0 1 0 0 1 0 0 1 0 0 0. It would look like this. Understood?
Yes, sir.
Because there are 4 flip-flops, and at a given time only one particular flip-flop state we are using to represent. So the representation of the 4 states would be, this will be 1 state, this is 2nd state, 3rd state, and 4th state. Okay. Naturally, the number of flip-flops required will be more over here. But this is the most preferred way because it gives a possibility of operating the state machine at a higher clock frequency. Okay. All right. Then how do you construct the modified state table? So we have already seen the state table. This was the state table. Now we are supposed to encode it properly. Okay. So that is what we will do. How do we construct the modified state table? So in our case, we will use the binary encoding. Obviously, there is no point in going for 1 hot and all that because it is a very simple state machine. So only one flip-flop will be necessary. Okay. So we assign low as 0, high as 1. Quite logical here. So I'm simply replacing over here as 0, 0, 1, 1. If you refer back to the state diagram, state table that we have already constructed. And then what we will do is we will fill up the rows, modify the rows in terms of the binary values. Okay. So conversion from this form to conversion to this form should not be very difficult to understand. All right. Is that fine?
Yes, sir. Yes.
This particular diagram. Okay. So what is the next step? Next step is derive the excitation equation. That is what we are going to do. Okay. So this is the modified state table, and from the modified state table, I am going to construct the excitation table. Now look at the excitation table. What exactly do you mean by excitation table? It is going to have these 4 columns here: present state, input, next state, and output. And of course, we are going to have 4 such rows corresponding to the transitions that we have already spoken about. All right. Look at this S and S star. S star is the next state. Okay. So how do you populate this table? Make a row entry. Go from here 0. Present state is 0. Input is 0. What is the next state? It is 0. Okay. The same time, when input was 0, output was also 0. So the very first entry becomes 0, 0, 0, 0. Are you able to understand this? That is the reason why I have drawn arrows over here so that you will be able to understand. What about the next row? When present state was 0, now there was an input asserted, that is 1. So the next state is going to be 1. So 0, input was 1, next state is 1, and correspondingly output is also equal to 1. Do you understand this?
Yes, sir.
Yes, sir.
Okay. Similarly, you can complete the remaining part of the excitation table. So what you get ultimately is this, which is called as the excitation table. All right. Is that fine?
Yes, sir.
Yes, sir.
All right. So this is what we got as the excitation table. Now we have to select the flip-flop. How do we select the flip-flop? In conventional design, there are various types of flip-flops available. You have the RS clock latch, you have JK flip-flop, D flip-flop, and T flip-flop. So RS clock flip-flop is generally used as a storage element. Okay. And of course, it is the fundamental building block of other types of flip-flop. JK, it's a versatile building block and be used to implement D and T flip-flops. D flip-flop is the simplest one. Okay. Its excitation table is also simple. So D flip-flop is mostly used in case of the state machines. Okay. Also in case of the FPGAs, CPLTs and the FPGAs, D flip-flop is used. Okay, so many times you'll see only the D flip-flop. Of course, there can be a multifunctional flip-flop, like flip-flop can develop as a latch also over there, but necessarily it works as a D flip-flop. Then T flip-flop, which is also called as a toggle flip-flop, it is constructed from the basic JK flip-flop and is best for the implementation of counters. Okay, so again, at the same time, it is also desirable to have the preset and the clear inputs for all the flip-flops. So in our case, D flip-flop is the best choice because it is simple. So logical design, as I said, the next step is the logic design for the output and the flip-flop inputs. So there are two outputs required over here. You can see these are the two, as this excitation table is nothing but a truth table. One truth table for next state, other truth table for the output. So what you have to do is, depending on the present state and input, so this is the truth table for one logic function, and this is the truth table. This inputs and this output together make truth table for the output. Okay, so what we do is we simply use the K map. This is for next state and logic function, and this is for the output logic function. So S star, you can see here simply that it is equal to I itself. Okay, you can use the logic minimization techniques and all those things that we have already, you must have already learned in your lower classes. The K map. Okay, output here in this case is what? S bar ANDed with I. This is what you get. So this is S bar. So what you have to do when you have one here in this case, S bar. So this is the sum of products. There's only one product here, by the way. So S bar and ANDed with I. All right. So this is what you get. So these are simple logic functions. So what do you get? Look at the way in which we have finally drawn the circuit diagram, the logic diagram. Input I. So if I want to generate the output, what should be the logic function for that? For output, it is S bar ANDed with I. So you can see here, this is the current state. This is the current state and it is inverted. So this is S bar ANDed with I to generate the output. Okay? And what about the next state? Next state is given as what?
It's I.
I itself. So you should see here that the D is connected directly to I. See if you can understand this. So this is how you design the state machine in a conventional fashion. Just have a look at it. Have you understood it? The design?
Yes,
Right?
sir.
Sure?
Yes.
Again, I want to warn here at this point of time that the present state and the next state scenario can be slightly confusing. So you have to be careful of that. Somebody would ask me if the next state, if the output is S bar ended with I, why are you showing this S star given as input over here? Did you have that question in mind?
Because we need complement of it.
Yes?
Because we need complement of it. No? S complement I. S complement ended with I.
No, not only that. How do I get the present state of the machine? The present state is nothing but this one. And this is going to be used for, we already seen that present state, S bar ended with I. So this is going to be the present state before the clock edge arrives. Are you getting this now?
Okay.
Yes?
Yes, sir.
Sure? Can be slightly confusing because this we have identified as next state. But this next state will be computed or maybe generated only at the arrival of the clock edge. Before that, it is the present state which has to be used over here. And then whenever I am having I here connected to D, naturally after the clock arrives, this next state will be decided by this input. ठीक है? Is that fine?
Yes, sir.
Shall we move on to a new state machine here?
Yes, sir.
At the same time, just keep in mind that the characteristic equation for D flip-flop is Q star, which is equal to D. That is Q output is equal to D. This will happen at the arrival of the clock edge. Yeah, this we are going to see as how to write the VHDL code for whatever we have seen right now. This was the conventional design, and this is what we are going to use while when we implement it using VHDL. So library IEEE library declaration, entity declaration. So in entity declaration, the name of that entity is edge underscore DET, edge detector, just short for that. You can write any name over here, you know that. Then what are the input ports? Reset, clock, and input. They are in mode and type bit. Similarly, I am going to have output as in out and bit, and there is going to be another more output out bit. We'll see why this is done. Not necessary, but okay. So how we are going to write the architecture? This is important. So what I'm going to do is I'm going to have a user defined custom type, and that type is called as state type and is low or high. So I'm enumerating these two definitions there. This is user defined data type, if you remember. Okay, and in state machine design, you have to use this type of declaration. Then I'm declaring a signal called as present state and next state. Okay. and they are belonging to what type? The state type, the type data type that I have declared over here. This is a user defined data type. So this signal present state, present underscore state and next underscore state is belonging to this type. So present state can take either only low or high, these two values. Similarly, next state will also be able to take only low or high, these two values. All right. Then I start with begin statement, and this is a label. Basically, it's not mandatory to use this, but it is easier this way. Process. I'm starting with the process. Now process. What do I say here? Process in bracket present state. What do you mean by that? Whatever is there inside the bracket in after process is what?
Sensitivity list.
Yes, it is. It is the sensitivity list. So this process will be executed if the state, if the value of this present underscore state changes anyway. Okay. Then begin the process begin, and then I'm using the case construct over here. The case present state is when low, what should happen? So read it like this. In case where present state is low, what should happen? Again, I am going to check for input. If input is 0, then I am going to make the next state is assigned as low, or else next state is assigned as high. Are you able to understand this first case? Guys? Guys, are you able to understand this?
Yes, sir.
Snehal, the lecture has started at 10 o'clock. You have joined very, very late. Snehal Patil. Of course, I am going to download the attendance now henceforth at the end of the lecture. Anyways, so continuing with this, we start with the process. Sensitivity list present state, begin, process begins, and I'm using a case construct over here, which is triggered when on present state, that is case present state is when low. So when present state is low, remember when present state is low, at that time if input is 0, the next state is assigned as low, else next state is assigned as high, and if. This should be fairly simple. Similarly, when your present state is high and if input is 0, the next state is low, else next state is high. Okay? Is this clear to all? This particular process?
Yes, sir.
Okay. This is one part where you change the states. So this is only assignment of the next state. This is only assignment of the next state. There has to be another process, okay, which we call here as the clocking process. So what should happen at the appearance of the clock? So process sensitivity clock begin if clock tick event and clock equal to 1. This simply means what? I am looking at the rising edge.
Rising edge.
So at the rising edge, what am I doing here? I am assigning what? Present state is assigned the next state that we have already computed, or which we have already got. So now present state is assigned the next state, and something called as Moore output is also assigned the output over there. Remember, whenever you talk about the Moore output, it will be synchronized to the clock. So it has to come in this particular clock process or clocking process. Okay. Now what about the output? We have not generated the output as yet. So this is called as a mealy output. In this another process, I am going to write input and present state. So this process is going to be executed when either input changes or present state changes. All right. Is that okay?
Yes, sir.
And then in that, what we are going to do, if present state is low and input is 1, then only this is the only combination where the output should be equal to 1. Otherwise, the output should remain 0. End process mealy output. So this is called as a 3-process style for writing the state machine. Go through this once again. This is the 3 process because there are 3 processes involved. So you can write the state machine, you can design the state machine using 3 processes. There is another style called as 2-process style. We'll see that subsequently. Just go through this once again and try to correlate it with the state diagram that we have seen. And of course, this is so, let us say, you can use it, you can create your own template for such a kind of thing. I'm going to tell that also. So you just have to understand, you just have to memorize the construct, that's all. State machine design using VHDL is very, very easy. ठीक है? Take a look at this. Why is the process called as mealy output? Guys, are you there with me?
Yes, sir.
Yes,
So why is it called as mealy output?
because the output of mealy machine depends on input and present state.
Not only that, it does not wait for the clock. Yeah, it does not wait
Yes,
for the
sir.
clock. If input changes or the present state changes anyhow, the output is going to be changed. Isn't it? ठीक है?
Yes, sir.
Okay. So if I synthesize this, this is the actual output that I get. So first of all, look at this synthesized output. See, we have this diagram with us. So try to correlate this diagram with what is synthesized by that software. Same thing, isn't it? See here. The additional thing that you get is this. Okay, why? Why do we get this? Because we want either to have the synchronized output, or you can directly have an unsynchronized or asynchronous output. This is your asynchronous output over here. So whenever your input changes, you can see here that the output is available, and this output is available only when the clock is available. Look at this. your input. This is exactly like what we have seen in our crude animation that I have already shown you right in the beginning. So this is the synthesized output. The D flip-flop you'll see here. Then you have the bubbled NAND like this for one particular input only. So the same inference. Got it? Are you able to see this properly? Understand this? Guys?
Yes, sir.
Okay. The next state machine that we are going to see is the sequence detector. Now this is a very popular uh, problem of detecting the sequence of or the patterns of the bits. So a state machine is to be designed to detect a sequence such that x is 0 followed by 1 followed by 0, 1 and 0. So it is going to detect a sequence called as 1 0 1 0. Okay, and the machine will generate high output only when it detects the proper sequence. After testing is complete, it starts all over again. So this is the word description. Okay, we are supposed to go for the state diagram. This is how the state diagram will look like. So just have a look at the state diagram. In my opinion, such a kind of sequence detector and all that, you draw the state diagram in a straight line like this. Okay, then it will be easy. So let us first of all see how many states are there and what exactly is going to be the output. So there are going to be 4 states. Because I am passing through this 4, checking each and every bit which follows, I am going to have 4 states. So in this state, this is the starting state. So if I detect a 0, okay, if I detect a 0, the state is not changed at all. And obviously there is no question of generating any output there. Okay, but if it detects 1, the very first bit of the sequence, it advances to the next state. Okay, so you'll see here, if it gets 1 as the input, output of course it is 0 because complete sequence has not been detected yet, but it advances to the next state. Now in the next state, this is going to be interesting. If it detects the next expected bit, that is 0, it will advance to the the third state. But if it detects a wrong bit, like 1 followed by 1, it falls back to the original state, the starting state, because it has no way started with the next state, with the sequence next bit in the sequence, and so on and so forth. So try to understand this. This is a very simple way of drawing, for especially for the sequence detector. Try to understand this, please.
Sir, I have a doubt at the
Yes.
last stage.
Last page. This one.
No. The next at the
This
state
one.
diagram. No. The current one. It was
This one.
right. This one after C at D 1 1. When will it stay at D only and not go back to A?
When will it stay?
At D only output is high now, right?
Yes. So what we are doing is we are detecting the sequence 1 0 1 and the next 0,
Right.
isn't it?
Yes.
So when it detects the last part of the sequence, it should stay over here and generate
Output high.
output. You can do one thing also, that as soon as it detects another 0, it again goes back to the original starting state. This is not the only solution. You can have multiple solutions.
Okay. Sir,
So it
after
depends on whether you want to find out an overlapping sequence.
right.
If you want to find out an overlapping sequence, if you want to detect an overlapping sequence, things will be different. Okay?
Okay. Right.
So this does not detect the overlapping sequence. Like now after this is it will not generate an output. The state diagram will be different for overlapping sequences. This is a very simple sequence detector. Okay? Is your doubt cleared?
Yes, sir.
Okay. So like our usual practice now, we have the state table from the state diagram. Try to understand how this is populated. Yes, now this is a more compact view of the state table. Earlier I have used a different, slightly different modification there. My own modification, by the way, to understand. But once you understand those things, creating such a state table will be easier. So there are 4 states, A, B, C, and D. Correspondingly, I have already encoded these states as 0, 0, 0, 1, 1, 0, and 1, 1. So the present state is directly shown here in the form of the encoded bits. Next state, obviously, this is going to be represented by again 0, 0. So 2 bits required for encoding the state. Okay. So the next state. So when present state is 0, 0 and your input is x. So input is 0. What should be the next state? It should be 0, 0. Okay. And the output also should be 0. Again, when the input is when the present state is 0, 0 and input was 1, the first bit of the sequence, then if input is 1, it should advance to the next state, that is 0, 1. All right. But again, the output remains 0, and so on and so forth. So try to figure out how the conversion from state diagram to state table has been done. Just try to do it on your own also and verify.
Sir, at when the present state is 1 1 and when the x is 0, if x continuously stays 0, then output will continuously stay 1.
Yes, that is going to be there.
Okay, so for next sequence to happen, it first has to go x equal to 1 and then again sequence
Yes,
will.
yes. That will be the start of the next sequence.
Okay.
ठीक है?
Yes, sir.
It would have made much more sense. Of course, as I said, this is not the only solution. If I detect a 0, okay, if I detect a 0, it will generate a 0, it will generate a 1, no doubt, but it does not stay here, but it goes back to A. That is one
Yes.
possible solution, isn't
Yes.
it?
Yes.
Yes.
Doesn't matter. ठीक है?
Yes, sir.
All right. So shall we move on to the next part?
Yes, sir.
So this is the excitation table. Just go through that. What exactly is required? So what do you have is the 8 states combinations, not the 8 states, 8 combinations. Okay. What is A, B, X and Y? What are these? These are simply these 2 bits. So call this as A, call this as B. Okay. And correspondingly output, of course, output you don't have to encode as 2 bits, it's only single bit. So output is this. So these are the inputs. These are the input. This is the A, B together make the present state. X is the input. A star, B star make the next state, and Y is the output. Understood? Look at the columns properly. So the blue part, what you see here, are the inputs. This is nothing but the truth table. That's all. This makes A star, B star together make the next state truth table, and this is the truth table for Y. Fine? Is that okay?
Yes, sir.
It is nothing but the representation of the same thing in form of the excitation table. Now again what we are going to do is use the K maps for reduction. This is how it is going to happen. So K map for next state A star, K map for next state B star. Okay. And finally K map for output Y. See if you understand this. Is it fine? Guys,
Yes, sir.
have you understood this? K map and all that you should have already
Yes, sir.
revised. So what we get ultimately is this. This is the hardware. Okay.
Yes, sir.
All right. Let us see the VHDL implementation. Again, we start with library declaration, entity declaration as well with the ports X, Y as input, X clock as input, Y as output, temp as in out, which I'm going to use over there. Then we have architecture. Please remember that we are always going to start with the type declaration. There are 4 states in our case. So I'm going to declare a state type, user defined data type as state type, and it is enumerated as A, B, C, and D. So it will have the possible values as A, B, C, and D. Signal I'm going to use as present state, next state, the same thing that we have done. Begin. Then this is the first process for with the sensitivity list as the present state. So this call this as the process when present state changes. This is going to be the very first thing every time. Again, I'm going to use the case construct over here. So when the present state is A, at the same time when X is 1, then you advance to the next state. Next state is assigned B, else it remains the same. Okay. When the present state is B, and if next state is, if input is 1, it goes back to A, otherwise it advances to C and so on. Try to understand this. Guys, are you there with me?
Yes, sir.
Okay, so have you understood this first process itself? Is this clear to all of you? This first process? Guys, please respond.
Yes, sir.
Okay, so then we go for the next process, the clocking process. Please remember, you will be having process for present state triggered by present state and process triggered by clock. Again, if clock tick event means rising edge, then next state is assigned to the present state, whatever we are having over there. So that then Y is assigned TEMP temp. We remember that temp is what? It is in out. Then finally, the mealy output process. X is your input and present state, and generally I am using this. So this is again a 3-process model, a 3-process style. So if present state is D and X is 0, then that is the last what do you call it? Pattern, a bit in the pattern. Then you generate a high, otherwise you generate a 0, and that's all. So do you see the pattern here for writing a state machine? All of you, please respond. Do you see a pattern here, guys?
Like
Sorry?
initially state type, then state clocking that way.
Yes.
Yeah. The same
So
thing was for previous as well.
exactly. So we have a template here, and it's very, very easy to remember that. So you should not find it difficult when attempting such a kind of problem. Okay?
Yes, sir.
Okay. This is what we get. Try to understand the timing diagram also. So you can see that the correct sequence generates y equal to 1, whereas incorrect. Now these are all state encodings, but the only thing is that you have to You will get these encodings only after synthesis. Simulation you may not get. This is the synthesis result. It has generated such a huge hardware. Okay. Anyway, this is all transparent for the user. So we need not worry about that. Okay. So let us have some kind of a template here. So Mealy state machine design procedure 1. Construct entity with input, output, reset, clock, in-out, which may be required for temporary storage. As far as possible, use the bit type. Declare states A, B, C, D. Declare signal present underscore state and next underscore state, or declarations between architecture and begin. And simulate only after synthesis. This is important because many times otherwise you will not be able to see the states over there. Like what we have seen here. States as 0, 1, 2 and 3. These 4 states will not be visible to you directly. If of course that is what I have found out, that it is easier, it will be visible only after synthesis, not before that. All right. So this is procedure number 1. This is the template. Just if you want, you can copy this down, the template. All right. And this is what we have already seen. This is called as a 3-process coding style. Okay.
Yes, sir.
All right. I think we'll stop here for today. We'll continue with the state machine in the next lecture. Okay. Meanwhile, I hope all of you have got your assignments. So start working from that point of view. Okay.
Yes, sir.
Yes, sir.